For this engagement check, we're going to be talking about the Earth and the Moon, the closest celestial bodies to us. We live on one of them. And here is a picture of the Earth and the Moon to scale. And we'll talk a little bit more about this in a later video. But you can see actually how pretty big our moon is compared to our Earth. And we actually have the largest moon to planet ratio any other planet in our solar system. But we're going to start by talking about the Earth first. So our Earth has an interior structure, just like whenever you peel open, if you ever cut up a baseball and look at it from like a cross section on the inside, it's made up of layers. Onions are made up of layers. Planets and stars too are made up of different layers. So for our Earth, we have an inner solid core in here made up of iron and nickel. So those are metals. And the solid core, so even though the temperature is really hot there, there's a lot of pressure pushing in on that core, and that's what's keeping that iron and nickel in a solid state. The inner core is about 10% of the Earth's radius, and it's about 5,500 degrees Celsius. It's really hot there, hot enough to be liquid, but again, that pressure of everything else of the Earth pushing in on it is what's keeping the iron and nickel as a solid. Then we have the outer core above that, which is also iron and nickel, but it's liquid. It's a liquid metal. And when you have liquid metals and you start to stir them up, you can generate an electric field. And as a byproduct, you can generate a magnetic field. So our Earth generates its magnetic field in this outer liquid metal core. Okay, and then on top of that, we have what's called the mantle. It's made up of something called silicate rock. We do say that the mantle is made up of rock, but the mantle of our Earth is such that over long periods of time, like tens of thousands of years, it can behave a little bit like a liquid. Think of like a really gloopy, thick kind of almost like a plastic. And then on top of that, we have the crust of the Earth. That's the thinnest layer. It's a solid layer of rock that floats on top of the mantle, and that's what we live on. Here's another example of Earth's interior. This is now a wedge. So our Earth's radius is about 6,371 kilometers. So here again, we have our solid core. We have our outer liquid core. The material in the outer core, that's the liquid metal, is doing something called convection. Okay, convection happens when you heat something on the bottom and it cools a little bit at the top. Kind of like when you have a pot of water on the stove, but it's not yet boiling. Hot, the stove top is warming up your water from the bottom. The hot water rises to the surface, it cools at the surface, and then it turns over again. And you set up these circular paths that we call convection currents. So the warm material is rising, cooling, and then coming back again. The stirring up of the material, the stirring it up and also spinning of the Earth is what's creating the magnetism. Okay, and then we have our mantle on top of that. And then we have our crust. The upper part of the mantle is called the asthenosphere. And this rock becomes ductile. If something's ductile, that means you can sort of stretch it a little bit. It's kind of pliable. So here we have the upper part of the mantle, the asthenosphere. And here we've got some convection currents that are also happening in this upper part of the mantle. Okay, and then the crust is floating on top of that. So then, due to convection, we have the crust, and the crust is broken up into different plates. These crustal plates can move around slowly, but still they move at about a few centimeters per year. That's about the same rate as our fingernails grow. You can just imagine that. So these plates, crustal plates, we also call them tectonic plates. There are 15 major tectonic plates today. These tectonic plates change over time. And so here's a picture, an image of how these tectonic plates are defined today. So let's see, the United States, North America is sitting on something that we just call the North American plate, okay? Here's one in the Caribbean. Here's a large one that's called the Pacific plate, where most of the Pacific Ocean is sitting above. The Eurasian plate, where we've got Europe and Asia on part of it, and also Russia, okay? It's the African plate, where, of course, Africa is sitting on top of. These are our modern tectonic plates. But over hundreds of millions of years, the tectonic plates have changed and moved. This is something that we call continental drift. And as a result, the Earth's land masses have moved around. These masses on the tectonic plates have moved around over time as well. So here, it's hard to see, but 225 million years ago, here's what all the land masses look like on our Earth. It creates this giant continent that we call Pangaea. And then over time, those plates move around, they shift, the land masses shift. And so you can see here that the African plate kind of starts to peel off from our South American plate. And then 65 million years ago, we start to see separation of the continents, more like what we see today. And now we're in present day. And now we see the continents as they are today. And what's really cool is that because we see how like Africa used to sort of be sitting up against South America, that when you look at the fossil records that date back to the Jurassic period when there was a lot of dinosaurs and stuff, you can find similar dinosaurs, similar fossils kind of on the boundaries of these tectonic plates. Today, you know, they're separated by this vast ocean, but 150 million years ago, they were not. Now, the Earth has a magnetic field. We're gonna learn a little bit about that in lab this week. I think magnetic fields of planets and stars are really cool. That's kind of what I did for my PhD. So we're gonna talk a little bit about it because it's kind of something that I'm interested in, so I get excited. So the Earth's magnetic field is like a giant bar magnet. If you've ever played around with bar magnets, or we'll get to do this in lab this week, the magnetic field that comes out of a bar magnet we call a dipolar magnetic field. Dipolar because there's two poles, okay, a north pole and a south pole of the magnet, okay. Now, so this is what we imagine it looks like, okay. Here's our bar magnet, and we've got the magnetic fields coming out of one end of the bar magnet, coming out of the north pole of the bar magnet, arching over and then connecting into the other side of the bar magnet, okay? So the magnetic fields come out of the north end of a bar magnet, they arch around, they come back into the south end of the bar magnet, okay? But for Earth's magnetic field, you can imagine that bar magnet, but actually the south pole end of your bar magnet is what is pointing toward what we call the geographic north pole of the Earth. So actually, okay, the geographic north pole of the Earth, the geomagnetic north pole of the Earth actually corresponds with the south pole end of a bar magnet. Now it's a little bit weird and confusing, but that's how it is. Like the north pole end of a bar magnet was named the North Pole end because if you kind of let that bar magnet hang stationary, and it will align with the Earth's magnetic field. And so the North Pole end of that bar magnet is going to point toward the geographic north. So like ends of a bar magnet repel, opposite ends of a bar magnet attract. So if we have our compass, which has a little magnet in it, and it's pointing toward north, the North Pole end of that bar magnet inside our compass wants to point toward the geomagnetic North Pole, which is actually the South Pole end of a very giant, you could imagine, bar magnet. Okay, so that's kind of how compasses work. And actually just remember that the geomagnetic North Pole of our Earth is actually a South Pole end, like the South Pole end of our bar magnet. The Earth's magnetic field meanders over time, it moves. And in particular, the Earth's geomagnetic poles wander over time. They're not perfectly aligned with the geographic north and south poles of the Earth. So we can see here that in the early 1900s, the Earth's geomagnetic North Pole was right here, kind of in Canada. But over time, it has shifted to be closer and closer and closer toward the pole of the geographic North Pole of our planet. And so our geomagnetic North Poles and South Poles have been meandering in unpredictable ways. It's hard for us to understand and predict. Our Earth's magnetic field is in its behavior and its change over time is not something that can be easily modeled. It is quite random, in fact, and that's a little bit annoying for us who do magnetic models of planets and stars, but that's just how the geodynamo inside our Earth behaves. Okay, so this red line shows how the Earth's geomagnetic North Pole has been changing over time. And down here, this red line shows how the South geomagnetic pole has been changing over time. Okay, so in the 1990s, the geomagnetic North Pole drift picked up from moving at about 15 kilometers per year to really booking it at changing at a rate of 55 kilometers per year. And we think the motion of the liquid metal and the Earth's outer core, changing that motion and stirring things up in a little bit of a different way, is causing that change in the location of Earth's geomagnetic poles. I mentioned this word called geodynamo, a dynamo. What is a dynamo? A dynamo is a process that converts mechanical energy, that's energy from motion, into magnetic energy. Okay, and so that's what's happening in our Earth's outer liquid metal core. So here we have a cross-section of our Earth. We've got the liquid metal core right here. And so giant rolls of the fluid, the liquid metal, inside the Earth's outer core are stirring around and spinning up, and that motion of that liquid metal generates a magnetic field. And from that motion, we get our Earth's large-scale magnetic field. So this is a picture, artist depiction of this. Over here is actually a computer simulation of an Earth-like geodynamo. And all these little spaghettis are lines of magnetism, magnetic field lines. And the colors represent the polarity. Is it a North Pole or a South Pole? So if it's like the Earth, we've got our magnetic field lines leaving from the magnetic North Pole down at the bottom here, arching over and then coming back up into the magnetic South Pole at the top here. Over time, it'll flip, and then you'll get go from south up, north down, to north up and south down, okay? And that process is also random too. It's random how we get these fluctuations and change of the Earth's polarity. We call this a geomagnetic reversal. The most recent geomagnetic reversal of the Earth happened around 780,000 years ago. But these reversals occur randomly, with intervals ranging from less than 0.1 million years to as much as 50 million years. So, you know, it's not real clear whenever it's going to happen for us again. So over here is the Earth's geomagnetic polarity over the past 5 million years. So we are way up here. And so if you see a black bar, that represents the polarity of the Earth that we have right now. So the last time it was different polarity was 780,000 years ago. And so you can see that actually in our modern polarity of the Earth, we've been in this state for a lot longer than at any other time in the past 5 million years, which is really interesting. Does that mean we're going to be due for a polarity reversal soon? Maybe. Will it be within our lifetime? Who knows? But what should generally happen is that if we're moving toward a geomagnetic polarity flip, the Earth's magnetic field will start to diminish a little bit over time. And at some point, it'll kind of be like it's almost not there for a little bit before it starts to build up and flip again. So during that time period, it might leave us as our planet a little bit more exposed. And so why do we care so much about magnetic field? The Earth's magnetic field protects us. We call the Earth's overall magnetic field the magnetosphere because our Earth's magnetic field fills the space around us. It's not just isolated very close to the Earth, fills up the space around us, okay? So here's our Earth. And remember we had that dipole shape, like the magnetic field coming from a bar magnet. And so what happens is that the sun has something called the solar wind, which is energetic stream of particles coming off of the sun, filling our solar system all the time. That stream of particles called the solar wind can actually peel back parts of that dipolar magnetic field. It peels back parts of that dipolar magnetic field and stretches them on the side that's away from the sun. And then you get this long tail of the magnetosphere, and you get this little front up here. And the whole time, the magnetic field of the Earth, the magnetosphere, shields us from these incoming solar particles. And the magnetosphere protects our atmosphere. It keeps our atmosphere from being blown away by the solar wind. Example, Mars. Mars doesn't have currently an active dynamo. It doesn't have this large scale magnetic field to protect it. And so it's losing a lot of its atmosphere over time because the solar wind is stripping it off because there's no magnetic field of Mars to protect it. And also, well, Mars is a little bit smaller than we are here. And so that planet, because it's less massive, can't hold on to as much of an atmosphere.